everyone. Welcome back to the course Introduction to Multi-Agent Systems. In the previous lecture, we talked about what are the conditions that are required for a system to achieve consensus while following the distributed averaging model. Note that an interesting property is that matrix A is always required to be semi-convergent whenever we want consensus. However, semi-convergence doesn't guarantee consensus. Sometimes the matrix A can be semi-convergent and we can get something that's known as disagreement in a system. So what exactly is the process of disagreement and what does the network look like when the agents are in a state of disagreement? So let's try to understand that in today's lecture. Consider the diagraph shown here. Let us consider the subgraph of nodes 2, 3, and 4. What can we observe? First, this subgraph is strongly connected. Not only that, the subgraph is also aperiodic. Why is it that way? It is because we see there are two cycles here. First is the simple self loop of length 1. So let's write cycles. First point is L of C1. The length of the first cycle is simply equal to 1. There's yet another cycle. The length of this cycle, let's call it C2, is equal to 3. The GCD of these lengths is equal to 1, which implies that the subgraph is aperiodic as well. Meaning, if we were to write up the adjacency matrix only for this subgraph, then that adjacency matrix would be primitive in nature. So from the previous lecture, we already know that any diagraph in this form where we have a strongly connected set of nodes forming an aperiodic subgraph which are globally reachable, meaning suppose we highlight now only this subgraph of nodes. We notice that we can start from anywhere and reach this subgraph, meaning this subgraph, which is strongly connected and aperiodic, is also globally reachable. Hence, from the previous lecture, we know that this network is going to achieve consensus among the states of all of the agents. So, let us write it. All the nodes achieve consensus. This is the first point. But at which value do they achieve consensus? That is, so the consensus, as we already know, is driven by the globally reachable nodes. In such a manner that states of all the agents converge to a value which is the weighted average of the initial conditions of only the globally reachable nodes. In other words, the nodes 1, 5, 6, and 7, the steady state values of 1, 5, 6, and 7 are governed by the weighted average of the states of 2, 3, and 4. Let us now consider the diagram shown here, which is a diagram different from the one that we just discussed. Different in what sense? Let's see. First of all, we see that none of the nodes are actually globally reachable here, right? On the other hand, there are certain nodes which are sink nodes in the condensation graph. So let us draw, to begin with, the condensation graph. The condensation graph takes a simple form where we replace every strongly connected component with a single node. So we see that there is one component here which is strongly connected, this. So we replace this entire thing with a strongly connected node. Now 4 and 5 appear as they are. 6 and 7 also are not associated with any strongly connected components and appear as they are. Now, if we observe here, 8 and 9 also form a strongly connected component. Hence, we again replace them with just one node. Let us add the arrows. And there's another arrow from here. And the last edge would be denoted in this manner. What do we observe here? Let's number them as A, B, C, D, E, and F. Which are the sinks here? We have two sinks, A and F. Notice that A is constituted of 3 nodes, which are 1, 2, and 3, and F is constituted by 8 and 9 in the original graph. So A and F belong to our condensation graph, and 1, 2, 3, and 8, 9 belong to the original graph. Since there are no globally reachable nodes, so if we apply the distributed averaging model, what is the kind of behavior that we'll get here? Again, let's pay attention to a few more things here. If we observe closely, node E takes all the information from F. Let's make a note of it. Node E, which is, if we see here, nothing but node 7. It takes all the information from node F, which is constituted by 8 and 9. Node D takes information from E, which in turn receives its information from F. So again, D, which is 6, receives information from the nodes 8 and 9, because whatever information E has, that is directly the information from F. So we can say implicitly 6 receives all of its information from 8 and 9. Similarly, if you look at node number C, it receives, C is node number 5 in the original graph. C, or 5, receives all of its information from node A, which simply consists of the nodes 1, 2, and 3. in the original graph. Node number B, which is nothing but node number 4 in the original graph, receives information again from node A in the condensation graph, which refers to the nodes 1, 2, and 3. What about the nodes A and F? A acts autonomously, meaning it doesn't receive information from any of the nodes. A, which is nothing but the nodes 1, 2, and 3. Similarly, F, which is nothing but the nodes 8 and 9, acts autonomously. Okay, so there's one thing here which is incorrect. Let me quickly correct that. Node number B actually receives information from two nodes, both A and E. Now, since E receives information from F, we write B receives information both from A and F. So what can we gather from this observation? We gather that the nodes 1, 2, and 3 act autonomously and propagate the information to nodes only B and C. Again, if you look at the nodes 8 and 9, 8 and 9 again act independently and they propagate their information to three nodes, which are B, D, and E. In the original graph, they are 4, 7, and 6. So obviously, consensus is not the outcome in this case. So what is the outcome? Notice that the node B, which is shown here, actually gets torn between two leaders which are trying to drive it, right? So B takes some information from A and some information from F. C takes all of its information from A, and the nodes D and E take all of the information from F. So if we try to draw, let us say this is where, just as an example, this is the steady state behavior along the x-axis, and this is the time parameter. The horizontal line in red is the steady state pertaining to the nodes or the sink A. Similarly, the one in green is the steady state of sink F. What happens to the node E? Now, the node E actually converges, has the same value as F at steady state, meaning the green also represents the steady state value of E and D. What about node number C? Node number C, on the other hand, receives information from A alone, meaning it converges to the same steady state as A. Let's write it. Something interesting happens with node number B. Note that node number B now receives information from both the sinks, A and F. Hence, its steady state value will lie somewhere as a weighted average of the steady state values of the sinks F and A. So this is of node B. Hence, the states or the agents are in disagreement. Okay. Now there's yet another important aspect since there are multiple sinks in the condensation graphs, there are multiple eigenvectors associated with the zero eigenvalue. Notice that it is 0 will now be a semi-simple eigenvalue, and it will have several eigenvectors which are associated, meaning consensus is not what we are going to achieve. So formally, how can we state this result? Let's see. We have been considering throughout this topic. Again, in this result, we begin by assuming A to be a row stochastic matrix and G being the associated digraph. And what is NS? This is something that we did not have in the previous result pertaining to a digraph having globally reachable set of nodes. So this NS is nothing but the number of sinks that are there in the condensation graph. Remember that when a digraph has a set of globally reachable nodes, then NS, the number of sinks in the condensation graph, is simply equal to 1. So here we are generalizing it to any value of NS, meaning the condensation can now have, let's say, several sinks. In that scenario, the following results become equivalent. So what are the results? Let's see. The first result says that the eigenvalue 1 now, rather than being simple, is now semi-simple. And its multiplicity is equal to NS. So the number of times the eigenvalue 1 is repeated is simply equal to the number of sinks that the condensation graph has. And as before, every other eigenvalue has a magnitude less than 1. The condition which is equivalent to this is the adjacency matrix in that case is again a semi-convergent matrix. And if these spectral properties hold, then the subgraphs of nodes which constitute the sinks of CG, every such graph is actually aperiodic. Again, what does the result say? It says that we have these nice spectral properties. What are the spectral properties? One is a semi-simple eigenvalue repeated ns number of times, and all of the other eigenvalues have magnitudes less than 1. This is only possible when the graph takes this form. The condensation graph has many sinks, and if all of the nodes which constitute these sinks actually obviously are strongly connected by definition, but not only that, they're also aperiodic in nature. Now, under these conditions, as we discussed using the example before, we do not get consensus. On the other hand, we get disagreement, right? But how exactly do we get disagreement? We talked about it using this graph. We know that nodes 6 and 7 converge directly to the steady state value that nodes 8 and 9 converge to. Node 5 again converges to the steady state value that the nodes 1, 2, and 3 converge to. Node number 4 does something different. It actually converges in such a manner that its output is some sort of a convex combination of both of these steady states pertaining to each of the subgraphs. Let us write it now formally. If any of the above conditions hold, then first thing that we can say is the left eigenvectors previously, remember, we just had one eigenvalue with value equal to 1, but now we have ns number of eigenvalues. Like the eigenvalue 1 is repeated ns number of times. So now we consider each of those corresponding left eigenvectors, and we denote them as sum wp, where obviously p belongs to the set 1 to ns. Okay, so the left eigenvector is wp of a corresponding to the eigenvalue 1 can be chosen such that first property is every wp is greater than or equal to 0. Second is the normalization property, which says 1n transpose wp is simply equal to 1. And the third property, which is now an important property, says that the ith entry of, let's write it in bracket, wp subscript I is nothing but the ith entry of wp. So this ith entry is greater than 0 only when there is a directed edge from node I sorry, please ignore this. Please delete this part. So WTP subscript I is greater than 0 only when the node I or the ith node belongs to the pth sink, belongs to or sink P. So the left eigenvectors, now all of the next left eigenvectors which satisfy. So let me add for completion that obviously, as always, each such left eigenvectors belongs to Rn. So all the left eigenvectors corresponding to the eigenvalue 1 satisfy all of these nice properties. In that case, we can now express our solution in the following manner. The solution, the solution of the distributed averaging model, which is nothing but x dot equals ax, is given by, we divide it into two parts. First is the ith entry of the state vector, let's write it as xi at steady state, denoted as xi bar, is equal to the value wp transpose times x0. When will this happen? Now this looks like the standard averaging thing. So obviously this only happens when node I belongs to sink P. Right? Only then consensus can be achieved. Second condition is that xi bar is in general given by alpha I comma p wp transpose x0. Notice that here we have a summation, and that summation runs from I to ns. So this happens otherwise. But we have to specify now some important conditions. But before we do, let us try to understand what this says. Now, we are summing over the solutions for each of the sinks. And what is the coefficient in this summation? It is the term alpha IP. So alpha IP tells us how much each sink contributes to the solution or the steady state value of the ith node. However, note that it is possible that sometimes only one of the sinks affects the nodes. For example, if we look here, we see that node 5 gets affected by only this strongly connected component. On the other hand, node number 4 actually gets affected by both of the strongly connected components, meaning the coefficient that we talked about should represent that 5 takes information from this subgraph alone and 4 takes information from both. So now we can express it in this manner. A very important condition is that the coefficient alpha I comma p is greater than 0. Only when there is a directed edge from node I to any of the sinks, any of the nodes, of sink P. So this makes complete sense. Now let's try to quickly understand this for the example that we have. In this example, the nodes 1, 2, 3 achieve consensus. The nodes 8 and 9 also achieve consensus. Let us say it achieves consensus at some value A bar, and this achieves consensus at some value F bar. Then for the node 3, alpha 3 comma P, or let's for the sink A. So just to remind you, we had this construction. A, B, C, D, E, and F. Now, the two sinks are A and F. So we'll have two eigenvalues. So let's write it here. Ns in our case is equal to 2. So we have two eigenvalues, left eigenvectors, W1 and W2 corresponding to each of them. Then alpha 5 comma A will be greater than 0, as there's a directed edge from 5 to 3, but alpha 5 comma f is equal to 0 because there's no directed edge from 5 to this thing f. Similarly, let's write it for node number 4. 4 comma a is greater than 0 because, as we can clearly see, there's a directed edge. And 4 comma f in this case is also greater than 0. But for node number 6, alpha 6 comma a is equal to 0 and alpha 6 comma f is greater than 0. There's just one node remaining. Let's write it for that. Alpha 7 comma a is again equal to 0 and alpha 7 comma f is greater than 0. So this is how we can predict or clearly say which of the nodes converge to which of the which of the leaders in the network. The leaders of the network are generally the sinks because they drive the opinions of the rest of the nodes. They drive the states of rest of the nodes in the network. So now we are using the term leaders for each of the strongly connected components in the digraph, or each of the sinks in the condensation graph, denoted as this. This is one strongly connected component. This is a different one. So the nodes 1, 2, 3, 8, and 9 are in some ways the leaders in the network. So this is one way in which we can figure out who are the leaders in the networks, because these are the nodes which contribute to the final states of all of the nodes in the network. However, there are many other ways in which we can figure out the leader or central nodes. So what are the ways in which we can do that? This is something that we will discuss in our next topic. So with this, we end our discussion on the averaging process. I hope you understand now in what cases we get consensus and in what cases we get disagreement. Thank you.